So now we know the basic formulas for the intercept coefficient b0 and the slope coefficient b1 for the line of best fit, or the linear regression, through our data. For the most part, we'll just let the computer work out the b0 and b1 for us, but in this lecture we're going to think a little more about those formulas and what they really mean. Let's start, because it's a little simpler, with the intercept formula. So here's the formula for that intercept coefficient b0, and it's not that exciting in a way, but we can say, well, we can notice first of all that it kind of has y bar and x bar snuck into it. That is, it's the same as this version here, because after all, y bar is just 1 over n times the sum of the yi's, and x bar is 1 over n times the sum of the xi's. So is that of interest to us? Well, it does mean that you can rewrite the regression line. So if we have a given value xi, and we want to know what's the y value on the line at that point xi, it's given by this formula here. So it's b0 plus b1 times xi. But if we rewrite that a little bit, we can see it's kind of like start at y bar, start at the mean of the y's, and then shift that according to how far your xi is from x bar, and then multiply that by the slope, which is the b1. So it gives us a bit of an intuition about what this line of best fit is all about. One thing it means in particular is if it so happened that xi was equal to x bar, that is, if we started at an x value right at the mean, well, then the corresponding y value, as you can see, would also be equal to y bar. So it means that the point x bar comma y bar is actually on the line of best fit. So we can see that this line that tries to match up all the points as well as possible, it always goes right through the mean of x and mean of y. That's always going to be a point on the line. Okay, so that's a little something about the intercept coefficient. What about the slope coefficient b1? Well, that's a little more complicated. Remember, the formula here is kind of a big mess, and we don't really understand it too well. Well, let's just start manipulating a bit. We can start by dividing top and bottom by n squared, and then it looks like this. Well, that doesn't look too much better, but we can see some x bar and y bars hidden in there. So now we can rewrite it like this, where x bar and y bar is the same as before. The next trick is to say, well, both numerator and denominator, they're a sum of products minus a sort of product of sums. Well, you can rewrite it this way, and you have to think about that for a second, because if you tried to multiply that out and sum it, you'd get some cross terms. But it turns out in both the top and the bottom, the cross terms kind of give you minus twice that final product, and then the final product there gives you one copy of it back. So you end up with the same minus x bar y bar in the numerator, or minus x bar squared in the denominator, same as before, and you can check that if you want. Then we can just cancel out the 1 over n's for a second and say, well, here's a formula for b1. And now let's do something that looks even a little crazier. So what I've done here is I've, first of all, separated out the denominator into its square root multiplied by its square root again. And then I've also multiplied and divided by this other square root, the square root of the sum of yi minus y bar squared. And it ends up what looks like an even messier formula than we had before. But then we can start to interpret it, because we can say, well, b1 now is that first crazy thing, which we'll call r, times this ratio, which we'll call s sub y over s sub x. And each of these factors is something that we've seen before. So this r here, well, it's this big crazy mess of a sum of xi minus x bar, y minus y bar over square root whatever. Well, that's a formula for the correlation between x and y. And we saw that way back when we were doing exploratory statistics. It's a measure of how much y tends to vary with x. So that makes perfect sense. Well, s sub x, that's just the sample standard deviation, or the square root of the sample variance for x. And similarly, s sub y is the sample standard deviation for y. So now we've kind of rewritten this big horrible formula for the slope coefficient b1, at least in terms of some things which are more familiar to us, even if they're not necessarily simple exactly. But that's going to turn out to be useful for us at times. Finally, let's talk about the residuals. So by residual, we'll mean the actual value that we observed minus the value that we would predict according to that line of best fit. So that is to say, the ith residual, we'll call it e sub i, and it's going to be y sub i minus what we would get on the line, namely the b0 plus b1 times xi. So you can rewrite it like this, and then we can start to learn some things about the residuals too. So what about the mean of all those residuals? Well, some of them might be positive, some of them might be negative. Here's a calculation for the mean. So the mean will then be the mean of the yi's, which is to say y bar, minus b0 minus b1 times the mean of the xi's, which is x bar. Now, if we just use, once again, that formula that we just derived for b0 and plug it in, then everything cancels out, and we get a mean of 0. So it means, yes, some of the residuals are positive, and some of them are negative, but their mean is 0, which kind of makes sense. It says that this line is trying to fit the data as well as possible, so it balances out. So on average, it hits it exactly. Sometimes it's too high, sometimes it's too low, but on average, it gets it right. Now, what about the variance of these residuals, these EIs? This turns out to be quite an important calculation. So we say, what's the variation in these EIs, the amount that's left over after we do our best line of best fit? Well, to do that, we need to do a little more algebraic manipulation, which I know you love so much. So we'll start out, here's the definition of EI. Then let's substitute in what we know for our formula for B0, and let's rewrite that a bit, and we can write it as yi minus y bar minus b1 times xi minus x bar. But then we can rewrite that and say, well, b1, we have this formula now, which is this r, this correlation, times sy divided by sx. So now we've got a formula for EI. Now let's look at EI minus E bar squared. Well, E bar, we just said, is equal to 0. So it's just EI squared. And we square that out. Now we do have cross terms, so we get this minus 2 times the cross term. And then we start computing for the variance. And the variance should be now the average, or 1 over n minus 1 times the sum of these things. And we start working it out, and we say, well, that yi minus y bar squared, when you take 1 over n minus 1 times that, that's just the variance of y, or sy squared. The second term is, again, this coefficient r times sy over sx squared, times this sx squared for the same reason. And then the cross term is, well, we've got a minus 2r sy over sx, but then we've got this sum of the xi minus x bars times yi minus y bars. So if we keep working away at that, we can say, well, this middle sum, that's kind of like a correlation again. And indeed, when we work it out and we stick in the values and normalize and everything, we get that the variance of E is the same as sy squared, well, that's the variance of y, times just 1 minus r squared, where r is this correlation coefficient again. So that is to say, when we put it all together, we can say the variance of the residuals E is equal to the variance of the y values, the yi's, multiplied by 1 minus r squared. So what does that mean? It means when you do regression, you kind of multiply the variance by 1 minus r squared, or once you take away the linear relationship, that removes or reduces a fraction r squared of the variance of y. And you can also, if you want to be fancier, say the linear relationship kind of explains a fraction r squared of the variation in y, and we're left over with just 1 minus r squared times the original variation. That's the variation in the residuals. Now this r squared is sometimes called the coefficient of determination, and you can think of it as saying what fraction of the variation in y has been explained by this linear relationship. Now if r squared equals 0, then that means, well, we didn't actually explain anything at all. There's no linear relationship between the y's and the x's, so we needn't have bothered. If r squared equals 1 at the other extreme, then that means the linear relationship explains everything. Once you know the x's, then you automatically know the y's completely. There's no leftover residuals. There's no leftover uncertainty. Usually it will be somewhere in between these two extremes, as you might expect. For our first example, let's go back again to the skeleton example where we were comparing the age difference, regressing that as a function of the BMI, the body mass index. And in that case, you can compute r squared either by working out the formulas that we talked about, or by computing the correlation and then squaring it, or by letting the computer do it for you. And one way or another, you figure out that the r squared is equal to 0.0186. Or in percent terms, you could say it's 1.86%. So that means in this case, the linear relationship is hardly explaining anything at all about the age difference. It's just explaining 1.86% of the variation that we get in this age difference can be explained by a linear relationship with the BMI. And that means that all the rest, over 98% of the variation, is not explained by BMI, and there must be more to the story. Let's do a second example, which is that GDP. So here we were considering the life expectancy of countries and territories around the world as a function of the GDP per capita of each of those countries. And that's the case. We already did the regression. Now we can compute the R squared again, either by using those formulas or by computing the correlation and squaring it, or probably by letting the computer do it for us. And in this case, we get a value of 0.4033, or just over 40%. So that's actually a much higher value, and it suggests that a fair bit of the variation in life expectancies in countries and territories around the world can indeed be explained by a linear relationship with the GDP per capita, or the wealth, of the different countries. And that's not so surprising. We've suspected for a while, and we've had some other evidence to suggest that indeed the GDP per capita is a fairly strong indicator of the life expectancy of a country. Now, it still doesn't explain everything because the R squared isn't 1, it's only equal to about 0.4, but it explains a fair bit. Now, we also notice that the relationship still doesn't look linear, as we said before, so once again, there's more to the story, and we'll come back to it again. But for now, we can see that R squared gives us some measure of how much of the variability is explained by the linear relationship. So in this lecture, we've learned a little more about those coefficients for the intercept and the slope of the linear regression, or the line of best fit. And we've also looked at the residuals, the E sub i's, and we've learned a little bit about how they are. For example, their mean is 0, and their variance can be computed in terms of the correlation and the standard deviations of the y and then the x. And then we saw finally that the linear relationship reduces the variance of the yi's. It multiplies it by 1 minus r squared, or it explains a fraction, r squared, of the variation.